Discussing the resonance concept. In the previous session that I started the concept of resonance in series circuits. How to see the continuation of that. All these introduction and some of the concepts with respect to resonance in series circuits I already explained. You please go through this who have not attended the sessions. This completed. How the inductive and capacitive reactances are varying with respect to frequency, and how to draw the net reactance curve with respect to frequency. All these that I already explained. And how the current and impedances are changing with respect to frequency in a series RLC circuit. Okay, all this I explained. You please go through this. And what is the variation of the power factor angle with respect to frequency? How the power factor angle is changing with respect to frequency in series RLC circuit. Now I'm starting. What is the variation of voltage across inductor and capacitor as a function of frequency? Here I have to calculate at what frequency the voltage across the inductor and voltage across the capacitor is maximum. In general, the voltage across the inductor and capacitor is not maximum at resonance frequency. It is maximum at some other frequency. Then at what frequency voltage across the inductor and voltage across the capacitor is maximum? And with respect to frequency, how the voltage across the inductor and capacitor is changing? Yes, I'm writing. Voltage across inductor. Yes. Voltage across inductor and voltage across capacitor. Voltage across capacitor is not maximum. Is not maximum at resonance frequency. At a resonance frequency. Voltage across inductor and voltage across capacitor is not maximum at a resonance frequency. It is maximum at some other frequency. It is maximum at some other frequency. It is maximum at some other frequency. Yes. Maximum at some other frequency. Students, we know that how to write the voltage across the capacitor. This I'm writing voltage across capacitor equal to voltage across capacitor. We know this VC equal to I into XC. Voltage across the capacitor VC equal to I into XC. But what is I? VC equal to this I equal to V by Z into XC. V by Z into XC. And we know this V by what is Z I written students? Square root R square plus XL minus XC whole square. R square plus XL minus XC whole square. This is into XC. This is into XC. This Z I am writing R square plus XL minus XC whole square. Then what is the voltage across the capacitor VC equal to? That is V by square root R square plus XL minus XC whole square. XL minus XC whole square. You have to write XC equal to 1 by omega C. X equal, that is capacitive reactance X equal to 1 by omega C. This is the voltage across the capacitor. Now to find frequency at which voltage across the capacitor is maximum, then what you have to do? To find frequency at which voltage across the capacitor is maximum. At which voltage across capacitor is maximum. Which voltage across capacitor is maximum. Maximum. Then what you can do? To find the condition for maxima, differentiate voltage across the capacitor with respect to omega and equate to 0. You have to differentiate voltage across the capacitor with respect to omega. This you have to differentiate with respect to omega and equate to 0. Then we can get the at what frequency the voltage across the capacitor is maximum. But I'm not giving the derivation. You have to do that differentiation and equate to 0 students. Then I'm directly writing what is the expression for frequency. Writing expression for frequency. That is voltage across the voltage across capacitor is maximum. Voltage across capacitor is maximum. Voltage across capacitor is maximum. Across capacitor is maximum. Maximum. At a frequency. At a frequency. Directly I'm writing. So how we can get that one? You differentiate with respect to omega and equate to 0. We can get a Fc equal to, write 1 by 2 pi square root, important formulas, 1 by Lc minus L into C, not L suffix C, that is L into C. 1 by Lc minus R square by 2L square. R square by 2L square squares. This is the frequency at which voltage across the capacitor is maximum. That is, at this frequency, the voltage across the capacitor is maximum. At this frequency, the voltage across the capacitor is maximum. You have to differentiate and equate to 0. We can get the expression for frequency, that is the voltage across the capacitor is maximum. Next. We can also write this frequency in terms of resonating frequency, Fc equal to, shall I write like this, friends? You take Lc is common. If you take Lc is common, 1 by 2 pi square root Lc, square root, this denominator Lc, that is 1 by Lc I'm taking common. If you bring 1 by Lc is common, that is 1 minus, this 1 by Lc is common, 1 minus, here there is no Lc, that's why R square into Lc by 2L square. R square into Lc by 2L square. Then if you simplify this, what is Fc equal to? Fc equal to 1 by 2 pi root Lc, 1 by 2 pi root Lc. This is square root 1 minus, square root 1 minus, this LL cancels, LL cancel, that is a R square C by 2L. R square C by 2L. Clear? I'm taking 1 by Lc is common. This is 1. Here Lc in denominator, but here there is no Lc here. That's why I'm writing into Lc. Then 1 minus R square into C by 2L. What is 1 by 2 pi root Lc? We know this 1 by 2 pi root Lc equal to F naught. That is a resonating frequency. Then Fc equal to F naught into square root 1 minus R square into C by 2L. This correction. Okay, this is the frequency at which voltage across the capacitor is maximum. At this frequency, the voltage across the capacitor is maximum. That is Fc equal to F naught into 1 minus square root R square C by 2L. This total is in the square root. R square C by 2L. What is F naught? F naught equal to 1 by 2 pi root L. Let this is also relation. How to remember, this is the 4. Clear, friends? Like this, I calculated at what frequency voltage across the capacitor is maximum. To find in RLC circuit at what frequency voltage across the capacitor is maximum, you have to differentiate and equate to 0. Then we are getting, this is the relation. It is not at F naught frequency. Voltage across the capacitor is maximum, not at F naught frequency. It is maximum at F naught into square root 1 minus R square into C by 2L. F naught into 1 minus square root R square into C by 2L. Similarly, you have to calculate at what frequency voltage across the inductor is maximum. At what frequency voltage across the inductor is maximum. Then how we can do? First write down what is the voltage across the inductor form. You have to write down voltage across the inductor form. How to write? Voltage across inductor equal to voltage across inductor. The voltage across inductor VL equal to I into XL. VL equal to I into XL. We know that this VL equal to I is V by Z. V by Z into XL. V by, what is the Z? Square root R square plus XL minus XC whole square into, what is XL, friends? XL equal to omega L. XL equal to omega. This is the voltage across the inductor. To find frequency at which voltage across the inductor is maximum, to get frequency at which voltage across the inductor is maximum, to get frequency at which voltage across the inductor is maximum, at which voltage across inductor is maximum, voltage across inductor is maximum. What you can do? You have to differentiate the VL with respect to omega and equate to 0. You differentiate this equation and equate to 0. If you differentiate that equation and equate to 0, then we can get directly, I'm writing, then FL equal to, this is the frequency at which voltage across the inductor is maximum, 1 by 2 pi into square root LC minus, that is LC minus R square C square by 2. R square C square by 2. Now from this you have to take the LC is common. This is the frequency at which voltage across the inductor is maximum. Frequency at which voltage across the inductor is maximum. So I taken this is the 3. Now take this is the 4 and this is the 5. Different relations. If you take LC is the common, students, then FL equal to 1 by 2 pi root LC, 2 pi root LC into square root 1 minus R square C square. But it is LC is not there here. Then you have to simplify this. That is R square C square by 2 LC. Here I am taking this LC is common. Here LC is not there. That's why divided by LC. This is equal to 1 by 2 pi root LC into square root 1 minus this C cancels R square C by 2L. R square C by 2L. Okay. Then what is 1 by 2 pi root LC? This 1 by 2 pi root LC is which one? F naught. This is F naught. Then you can write FL equal to F naught by square root 1 minus R square C by 2L. This is the frequency at which voltage across the inductor is maximum. Different ways of representing. This FC equal to F naught into 1 minus square root R square C by 2L. But here FL equal to F naught by 1 minus R square C by 2L. Easy to remember. This is multiplying here. Here it is a dividing. 1 minus R square C by 2L. Okay, this is the voltage across the inductor is maximum at a frequency FL. Voltage across the capacitor is maximum at a frequency. Voltage across the capacitor is maximum at a frequency FC. That is, if you draw the characteristics, this one. Now, if you draw the characteristics here, what is FC? That is the frequency at which voltage across the inductor is maximum. FC equal to F naught into square root 1 minus R square C by 2L. What is FL? FL equal to F naught by square root 1 minus R square C by 2L. This is FL and FC. Now, if you draw the characteristics for this, we are drawing the characteristics for frequency versus VC and VL slopes. VC and voltage across the inductor, voltage across the capacitor. Now tell, for F less than F naught, let this is the resonating frequency. This is F equal to F naught. See, if you substitute F equal to, that is FC equal to F naught, FL equal to F naught, at F equal to F naught, this is the resonating frequency. For F less than F naught, for lower frequencies, for F less than F naught, which is dominant here? For F less than F naught, which is dominant? That is for F less than F naught, which is the dominant. Or for FC less than F naught. For FC less than F naught. For FC less than F naught. If you take FC less than F naught, this is FC less than F naught. Then if FC less than F naught, frequency at VL is maximum. Frequency at VL is maximum. If you draw the characteristics for this case, this indicates the VC characteristics. This indicates VC characteristics. And this indicates VL characteristics. This indicates VL characteristics. Clear? If you draw the characteristics for different frequencies, then this indicates the VC characteristics. That is, this frequency is maximum. The voltage is maximum at FC. This voltage is maximum at FM. And this is the resonating frequency. This is the resonating frequency. This is the resonating frequency. This is FC. This is less than F naught. For FC less than F naught. For FC less than F naught, which is maximum? VC is maximum. Correct? VC is maximum. For different values of frequency, if you draw the characteristics, then we can get this one. VC characteristics, and this is the VL characteristics. For FC less than F naught, this is F naught. FC less than F naught, which is maximum? VC maximum. FC less than F naught, VC is maximum. Next, for FC, this one, FL greater than F naught. This is greater than the resonating frequency now. FL greater than F naught, which is maximum. Voltage across the inductor is maximum. VL is maximum. This is the observation. Writing. Or write down. VL is maximum. Clear? This is VL characteristics and these are the VC characteristics. If you see this characteristics for FC less than F naught, that is this frequency is less than F naught and this frequency is greater than F naught. This frequency is the resonating frequency. That is what the final conclusion here. Not writing. What the final conclusion here? Sorry, sir. Pen is not writing proper. Just a minute. The final conclusion is voltage across the capacitor is maximum for less than resonating frequency. That frequency is FC. Voltage across the inductor is maximum for greater than resonating frequency. That frequency is the FL. That point you have to remember. Clear, friends? That point you have to remember. The next one is one more topic with respect to resonance concept. That is the quality factor. What is the quality factor? We know that in a tuned circuits, we are using L and C elements. Whatever the L and C elements we are using in the tuned circuits, that is one of the application. In tuned circuit, resonance concept is used in tuned circuits. A resonance concept is nothing but a rate of transfer of energy between the L and C elements. The components L and C is used in the tuned circuits. Whatever the L and C elements we are using in the tuned circuits, that inductive coil and capacitive coil must have high quality. Then whatever the L and C coils we are using, how much quality is there? Is it a high quality coils or low Q coil, low quality coils? Is it a high figure of merit or low figure of merit? Is defined by quality factor. Say, for example, in a particular tuned circuits, we are using inductors and capacitors. Whatever the inductors we are used, is it a high quality inductors or low quality inductors? Is it a high quality capacitors or low quality capacitors? That is measured by quality factor. This I given. Components L and C used in a tuned circuit must have high quality, which is defined as quality factor or figure of merit of a coil. That is called a quality factor or figure of merit of a coil. Quality factor indicates the quality factor. This is some mistake here. Quality factor is right. Quality factor indicates the quality of a coil. It indicates the quality of a coil. Quality factor indicates the quality of a coil. Quality factor is ratio of maximum energy stored in the circuit to energy dissipated per cycle. This is important. This is the fundamental formula for quality factor. Very important. The fundamental formula for quality factor equal to maximum energy stored by energy dissipated per cycle. If energy dissipated per cycle is more in any coil, if there is more energy dissipation, then that coil is having the low quality factor. If energy dissipation is less, then we can say that that coil is having the high quality factor. That's why the fundamental formula for quality factor equal to maximum energy stored by energy dissipated per cycle into 2 pi. Why I multiplied with into 2 pi? This is defined for per cycle. The another way to understand, friends, if any coil is storing the maximum energy, more energy, then we can say that that coil is having the high quality. If any coil is storing the less energy, then that is having the low quality factor. It is also defined the ratio of voltage across the inductor or voltage across the capacitor to supply voltage at resonance condition. That means the quality factor is also defined as voltage across the inductor by supply voltage or voltage across the capacitor by supply voltage. You have to define voltage across the inductor by supply voltage or voltage across the capacitor by supply voltage. That is, you define quality factor Q equal to VL by V. Students, we know that VL equal to I into XL. But you know that XL equal to XC at resonance condition, na? I into XC by V. That is equal to VC by V. Very important. This is one more formula for quality factor. That is voltage across the inductor by supply voltage or voltage across the capacitor by supply voltage. It is at which condition? At resonance condition. At a resonance condition. Why you are defining the quality factor? To measure the quality of a coil. To measure the quality of a coil. Then at resonance condition, the quality factor equal to voltage across the inductor by supply voltage or voltage across the capacitor by supply voltage. Now I have to give some important formulas with respect to quality factor. That is very important. That is, we know that quality factor Q equal to VL by V. This is one formula, you know, VL by V. Then shall I write like this? VL equal to, we know that at resonance condition, current is maximum. Current is maximum. At resonance, current is maximum. Let that maximum current I naught equal to I max equal to, at resonance condition, what is the current? V by R. Because Z equal to R. At resonance condition, Z equal to R. I am writing VL equal to I naught into XL by V. I naught into XL, that is by V. I am writing voltage across the inductor at resonance condition equal to I naught into XL. That you can also write like this, I naught into XL by, what is V? I naught into R. I naught into R. This I naught cancel. Then one more formula for quality factor equal to XL by R. What is XL? Omega L. That is by R. XL equal to omega L. That is omega L by R squares. It is at resonance condition. That's why I'm taking omega naught into L. All these are I'm defining at resonance condition. At resonance condition, we know the angular frequency is omega naught. That is omega naught into L by R. How to write omega naught? 1 by root LC. Omega naught equal to 1 by root LC into L by R. If you simplify this, what you can get? 1 by R into square root L by C students. 1 by R into square root L. This is one more formula for quality. 1 by R into square root L. You have to take XL by R, omega naught into L by R, or 1 by R into square root L by C. This is for with respect to inductor. This is the quality factor. Next, we can also define quality factor like this. Q equal to VC by V. One more formula for quality factor is VC by V. Shall I write like this? I naught into XC by I naught into R. This is equal to XC by R. Therefore, quality factor equal to XC by R students. That is how to write XC? 1 by omega naught into C. 1 by omega C na. But this is at resonance. All these are resonance condition. The quality factor is defining at resonance condition. At a resonance condition. I am writing X equal to 1 by omega C. That is omega C R. XC by R, 1 by omega C R. But you can write omega naught equal to 1 by root LC into CR. 1 by root LC into CR. If you simplify this, then we can get 1 by R into root LC. Finally, we are getting 1 by R into root L by C. Okay, this is the quality. Okay, this is the one more formula for quality of a coil. Clear? So, for example, this note point I am giving students that you have to concentrate. If pure resistor is there, can anybody tell what is the quality factor? If it is a resistor means it is not a coil, there is no inductance. Then pure resistor, the quality factor is 0. If it is a pure inductor means the energy dissipation is 0. If energy dissipation is 0, then what is the quality factor, sir? Quality factor is infinity. Pure inductor quality, practically it is not infinity, na? But pure inductor is not possible. The quality factor is infinity because pure inductor. No energy dissipation, no energy dissipation. Energy dissipation is 0. This is the fundamental formula you have to apply. If the energy dissipation is 0, quality factor is infinity. If it is a pure capacitor, students, what is the quality factor? Is also infinity. There is no energy dissipation. If it is a series RL combination, the quality factor Q equal to omega naught into L by R. This is the series RL combination. If it is a series RC combination, students, how to write the quality factor equal to 1 by omega naught into CR. 1 by omega naught into CR. Next, if it is a RLC combination, if there is a RLC combination, then you can write the quality factor is like this: 1 by R into square root L by C. All these are the quality factor formulas. If it is a parallel RL combination, like this it is given, then you have to write the quality factor equal to R by omega naught into L. R by omega naught into L. If it is a parallel RC combination, exactly opposite. For this and this opposite. Parallel RC combination. Then what is the quality factor you have to write? That is omega naught into R into C. This 1 by omega naught CR, this is omega naught. This reverse you have to write. The derivations are there but not required. If it is a parallel RLC combination, can you write what the quality factor? If it is a parallel RLC combination, what the this exactly inverse of this one, series inverse you write. Then R into square root, this inverse na R. This reverse you can take C by L. These are the quality factors for series combination and parallel combination. But point to remember, students, given coils are high quality factor coils, are low quality factor coils, are medium Q coils. How to identify? That is based on quality factor, the coils are classified into three types. This is also important observation. Based on quality factor, based on quality factor, the coils are classified into, the coils are classified into, one is low Q coils, low quality factor coils. When the particular coils are said to be low Q coils, if the quality factor is less than or equal to 1, those are called low Q coils. Medium Q coils, when the particular coils are said to be medium quality factor coils. Medium Q coils. This 1 less than Q, less than or equal to 10 is treated as a medium Q coils. When the particular coils are said to be high Q coils, high quality factor coils. When the quality factor is greater than 10, those coils are said to be high Q coils. These are the points you have to remember with respect to quality factor of a coils. Clear? But here, how to give one more important observation. Then we can prove that a series RLC resonance circuit, a series resonance circuit is a voltage magnification circuit, or it is also called acceptor circuit. Then how to say that it is a voltage magnification circuit or acceptor circuit? Voltage magnification circuit or acceptor circuit. We know that voltage across the inductor and voltage across the capacitor. Students, at resonance condition, at resonance XL equal to XC. At resonance XL equal to XC. Okay, this you know. I given proof already. Then what is the voltage across inductor? Voltage across inductor, you write. Voltage across inductor equal to, that is I naught into XL. Let the current at resonance condition is I naught, then I naught into XL. This is VL. Therefore, VL equal to, how to write I naught? I naught equal to V by R. At resonance condition, I naught equal to V by R, because Z equal to R now. That's why V by R into XL. Shall I write XL equal to omega naught into L? That is omega naught into L by R into V. But what is omega naught into L by R? I already defined. That is the quality factor. VL equal to QV. That is voltage across the inductor equal to Q times of the supply voltage. Voltage across the inductor equal to Q times of the supply voltage, where V is the supply voltage. Supply voltage. Similarly, if you write the voltage across capacitor, if you write voltage across capacitor, sir. If you write the voltage across the capacitor, what is VC equal to I naught into XC? This is all these are at resonance condition. What is I naught? V by R into XC. How to write XC? XC equal to 1 by omega naught C. At resonance condition. 1 by omega naught into CR into V. But what is 1 by omega naught CR? It is also Q. VC equal to this. I written a quality factor formula, friends. Yes, sir. This 1 by omega naught into CR equal to quality factor. Omega naught into L by R is also quality factor. Okay, that you have to substitute here. Yeah, then if you write a QV, VC equal to Q. That is voltage across the inductor is also QV, and voltage across the capacitor is also Q into V. Then what is the observation here? This is VL equal to Q into V. VC is also Q into V, where Q is the quality. That is, at series resonance condition, voltage across inductor and capacitor is Q times the supply voltage. Q times the supply voltage. Hence, it is treated as a voltage magnification circuit. We can voltage mag, it is a Q times of the supply voltage. Then by varying this Q, quality factor of a coil, we can vary the voltage across the inductor and we can vary the voltage across the. That's why it is treated as a voltage magnification circuit. Students, we know that at resonance condition, net impedance is minimum. I told already, at resonance condition, Z equal to R, this is Z minimum. At resonance, I already explained the previous session. And what the current? Current is maximum. That is, in this circuit, at resonance condition, current is flowing maximum current. Maximum current is flowing means it allowing the high currents, it accepting the high currents. That's why it is treated as acceptor circuit. We can magnify voltage across the inductor and capacitor. This it depends on the quality factor. At series resonance condition, net impedance is minimum and current is maximum. If impedance is minimum and current is maximum, then that resonance circuit is treated as acceptor circuit. That's why series resonance circuit is acceptor circuit and it is a voltage magnification circuit. For this is the explanation, students, that you have to concentrate. Yeah, this one more observation at resonance condition. Next, I have to define what is the bandwidth and cutoff frequencies. What is the bandwidth and the cutoff frequencies, friends? This one more topic. Bandwidth and cutoff frequencies in a series resonance circuit. Bandwidth represents range of frequencies for which power level in the signal is at least half of maximum power that circuits can handle. That is, bandwidth represents the range of frequencies for this frequency range, for the frequency ranges for which power level in the signal is at least half of the maximum power. Minimum, sorry, half of the maximum power is handled. For that frequencies, that range of frequencies is treated as a band. When the curve is drawn between the current and frequency, the curve is called a resonance curve. Bandwidth is the range of frequencies for which current is equal to 70.7% of the maximum. With respect to powers, half of the power. With respect to current, 70.7% of maximum. That is I maximum by root. At that frequencies only, we can define the bandwidth flares. That we'll see in detail. With respect to powers, we have to define at a half of the power. With respect to current, we have to define at the maximum. We have to define at the maximum. That is a maxima current by root. That is, I am drawing this curve. We know that I naught equal to V by R. I naught equal to V by R. Then at cutoff frequency, friends, at cutoff frequency, what the magnitude of current? I'm not talking about with respect to power. With respect to current, I'm talking. The magnitude of current equal to I naught by root 2. Maximum current by root 2. That is I max by root. I naught is nothing but I max here. I max by root. That is at a cutoff frequency. This is the I naught. We know that at resonance condition, current is maximum. This is I naught. This is I naught. This is at what frequency? Resonating frequency, omega. Let omega 1 and omega 2 are the cutoff frequencies. Omega 1 and omega 2 are the cutoff frequencies. At cutoff frequencies, what the current should? This is the definition. At cutoff frequencies, this is I naught by root. Maximum current by root. This is at the cutoff frequencies. That is I naught by root. That is the magnitude of current equal to I naught by root. Then this is treated, this frequency range is treated as which one? This is called bandwidth. These frequency ranges are treated. This is the definition. These frequency ranges are treated as a band. Friends, we know that this is omega naught. This is xc greater than xl. Already given at starting. For frequency less than resonating frequency, capacitive is dominant. This is the xc greater than xl. And this is for xl greater than xc. Again, don't ask how it is. You please go through the starting class. This xc greater than xl and this is xl greater than xc. This side is xc greater than xl. Now this is which one? Leading. And this is for lagging. Every observation already given. Please go through this. Bandwidth. Now, how to find what the expression for bandwidth and what is the relation between bandwidth and resonating frequencies? For this, small observations that I have expressed. Listen. At cutoff frequency, the magnitude of current equal to maximum current by root 2. Then what is the magnitude of current? That is modulus of I equal to I naught by root 2. Na? What is the magnitude of current, friends? V by square root R square plus the total current. That is XL in RLC circuit. R square plus XL by XC whole square. This is equal to, what is I naught? I naught equal to V by R into 1 by root 2. I naught equal to V by R, na? That is 1 by root 2. Then this V cancels. Then from this, what you write? Square root R square plus, very important relations we can get here, XL minus XC whole square is equal to root 2 times of R. XL minus XC whole square, that is root 2 times of R. Then square on both sides, R square plus XL minus XC whole square is equal to 2R square. Square on both sides, friends, 2R square. If you square on both sides, root will be cancelled, it is a 2R square. Then what is XL minus XC whole square equal to? That is R square. You bring this R square this side, R square you can get. What is XL minus XC equal to? Plus R minus R. XL minus XC equal to plus R minus R. This is XL minus XC. That is XL minus XC equal to plus R minus R we are getting. Now what are the observations? That is XL minus XC equal to plus R minus R. Then shall I write like this? What is XL? Omega L. What is XC? Here I am writing to derive the bandwidth. XL equal to omega L. XC equal to 1 by omega C. This is equal to plus R minus R. Correct? Plus R minus R. At omega equal to omega 1. At omega equal to omega 1, sir. That is, omega 1 is the lower cutoff frequency. Omega 2 is the upper cutoff frequency. Point to remember. This is the lower cutoff frequency. Lower cutoff frequency. I'm writing in terms of angular frequency. Lower cutoff frequency. This is Omega 2 is which one? It's the upper cutoff frequency. This is upper cutoff frequency. Upper cutoff frequency. Okay. Now tell me, at omega equal to omega 1 means lower cutoff frequency. For lower cutoff frequency, which is the dominant? Xc greater than XL. Xc greater than XL. That you know. For lower cutoff frequency, Xc greater than XL. Now, if Xc greater than XL, this difference becomes positive or negative. First, I'm defining at lower cutoff frequency. Na? At lower cutoff frequency, this you take positive or negative. Because Fc greater than XL, na? Xc greater than XL means negative. Xc greater than, this is Xc greater than XL means negative. That's why substitute omega equal to omega 1. Omega 1 into L minus 1 by omega 1 into C is equal to, you take minus R plus R. You take minus R. Why? Because for lower cutoff frequency, Xc greater than XL, if it is Xc greater than XL, this difference becomes negative. That's why taken as a minus R. Let this is the relation one students. This is the relation. Next. At omega equal to omega 2. At omega equal to omega 2. That is upper cutoff frequency. Now tell me. For upper cutoff frequency, this is upper cutoff frequency. Now, which is greater? XL greater than XC. Then XL greater than XC. Then what is that difference, students? What this difference becomes? Now, XL greater than means this is greater. Then this difference becomes positive. Then you substitute this, substitute omega 2 here. Substitute omega 2. Then omega 2 into L minus 1 by omega 2 into C is equal to plus R. Because it's a positive. This is plus R you can get. Then you take this is equation 2. Equation 2. Now we have to do 1 plus 2. Very important relation we can get. For this, I am doing this here. 1 plus 2. Then what is 1 plus 2? That is omega 1 into L minus 1 by omega 1 into C plus omega 2 into L minus 1 by omega t into C. 1 plus 2, if you do minus R plus R, this right side minus R plus R equal to 0. That is equal to 0. Clear? Then take a L is common here. If you take L is common, omega 1 plus omega 2. You bring this side, take the 1 by C is common. If you take 1 by C is common, 1 by omega 1 plus 1 by omega 2 students. Then if you simplify this, what you can get? That is L into omega 1 plus omega 2. L into omega 1 plus omega 2. This is equal to 1 by C into LCM is omega 1 into omega 2. That is omega 1 plus omega 2 by omega 1 into omega 2. Students. Then this term and this term cancel. Then from this, what you can write? There's L equal to 1 by C into omega 1 plus omega. Sorry, omega 1 into omega. Omega 1 into omega. Correct? Omega 1 into omega. Then from this, what is omega 1 into omega 2, students? 1 by LC I got. But you know that omega naught equal to 1 by root LC. Omega naught equal to 1 by root LC. From this, what is omega naught square equal to 1 by LC? Then I'm replacing this 1 by LC equal to omega naught square. Therefore, very important observation that you have to concentrate. Then omega naught square equal to omega 1 into omega 2. Then from this, what is omega naught, friends? From this, what is omega naught? This omega naught equal to square root omega 1 into omega 2. Omega 1. This is important observation. That is the relation between resonating frequencies and cutoff frequencies. Relation between resonating frequencies and cutoff frequencies. That is resonance frequency is the geometric mean of cutoff frequencies. Therefore, resonance frequency is the geometric mean of cutoff frequencies. You can also write like this now. Omega naught is 2 pi f naught. This is equal to 2 pi f1 in terms of cutoff frequencies. 2 pi f1 into omega 2 is also 2 pi f2. Then if you simplify this, f naught equal to what you can get, friends? Square root f1 into f2. Square root f1 into f2. Then what the statement you have to write? Then resonating frequency equal to geometric mean of cutoff frequencies. Geometric mean of cutoff frequencies. Therefore, resonance frequency equal to resonance frequencies. Write that statement. Resonance frequency is the geometric mean of cutoff frequencies. Is the geometric mean of cutoff frequencies. Geometric mean of cutoff frequencies. F1 is the lower cutoff frequency, F2 is the upper cutoff frequency. Even that is in frequency in hertz. Omega 1, omega 2 also, that is angular frequencies. Geometric mean of cutoff frequencies. Geometric mean of, not right up, it's a cutoff frequencies. Cutoff frequencies. Resonance frequency is the geometric mean of cutoff frequencies. Okay, that statement. For this formula only, I derived this. Okay, this concept. And how to find the what is the formula for bandwidth? What is the formula for bandwidth? And to find the formula for bandwidth, you have to do this equation. To find the formula. Then you do this one. So it's 2 minus 1 I'm doing. Next I'm doing the 2 minus 1. What is 2? Omega 2 into L minus 1 by omega 2 into C. This is the 2 minus, what is the 1? Omega 1 into L minus 1 by omega 1 into C. This is equal to 2 is R. Then minus 1 is minus R. Minus R plus R, that is 2R. That is the 2R. Then if you simplify this one, take L is common. Omega 2 minus omega 1. Omega 2 minus 1. Omega 1. Take the 1 by C is common, friends. It's 1 by C is common. If you take 1 by C is common, we can get 1 by omega 1 minus 1 by omega 2 is equal to 2R. Is equal to 2R. Then you simplify this L into omega 2 minus omega 1 plus 1 by C into, this is omega 2 minus omega 1 by omega 1 into omega 1, omega 1 into omega 2 is derivation. Take omega 2 minus omega 1 is common. If you take the omega 2 minus omega 1 is common, friends, what do you get? L plus 1 by C into 1 by omega 1 into omega is equal to 2R. Then omega 2 minus omega 1 into L plus 1 by C. What is omega 1 into omega 2? This is omega naught square. This already you know. This omega naught square equal to omega 1 into omega 2 into 2R equal to 2R. What is omega naught square, friends? 1 by LC. Step by step I am explaining. But final observation is important, not the derivation. Just for concept point of I am doing this. L plus 1 by C into omega naught square equal to 1 by LC is equal to 2R, friends. Then CC cancel. Then what you can get? Omega 2 minus omega 1 into, this is L goes to the numerator. L plus L to L is equal to 2R. Equal to 2R. Then from this 2 cancel. What omega 2 minus omega 1 you can get? Then omega 2 minus omega 1. Omega 2 minus omega 1 equal to, we are getting R by L. This omega 2 minus omega 1, this is difference between upper cutoff frequency and lower cutoff frequency. What is the difference between upper cutoff frequency and lower cutoff frequency? This is called bandwidth. What is the bandwidth here, sir? This is the bandwidth now. Bandwidth equal to, what is the formula? The upper cutoff frequency and lower cutoff. This difference is the bandwidth. This is the bandwidth equal to how much here? Omega 2 minus omega 1. Omega 2 minus omega. This I derived. What is omega 2 minus omega 1 I got? R by L. This is called bandwidth. This is called bandwidth. Then we can also, this is one formula for bandwidth in terms of angular frequencies, angular cutoff frequencies. In terms of angular cutoff frequencies, that is bandwidth equal to omega 2 minus omega 1. This is equal to R by L. We can also write bandwidth equal to, what is omega 2? 2 pi f2. What is omega 1? 2 pi f1 is equal to R by L. 2 pi f2, that is 2 pi f1, that is equal to R by L. Then from this, what you can write, friends? Bandwidth equal to f2 minus f1 is equal to, take the 2 pi is common, you bring this side, R by 2 pi L. R by 2. This is one more form. If you write in terms of the f2 and f1, we can get the bandwidth equal to R by 2 pi. But if you write in terms of omega 2 and omega 1, you get the bandwidth equal to R by L. This is the bandwidth and this is also bandwidth. Clear? That is bandwidth equal to, we are getting, that is R by 2 pi f, R by L and R by 2 pi. Okay, that you have to concentrate. Okay, this is about how to derive the that is voltage at the frequency at which voltage across the inductor is maximum, the frequency at which voltage across the capacitor is maximum. Then what is the concept of quality factor and how to derive the bandwidth and what is the resonating frequency is the geometric mean of the cutoff frequencies that happen. Now, with this knowledge, you have to calculate what are the cutoff frequencies. Once you know the bandwidth, you have to calculate the cutoff frequencies, friends. You have to calculate the cutoff frequencies. Yes. This is okay. Any doubt? Yeah. Now I'm ending the session because next one more class is there. You have to take a break, then you continue with that other class. Okay. Then next coming session, I will explain how to calculate the cutoff frequencies. Still now I explain only up to bandwidth. Then how to calculate the cutoff frequencies also I will explain. That is omega 1 and omega 2 equation. Then I have to discuss with respect to series resonance itself, power factor and cutoff frequencies relation. And what is the relation between quality factor and bandwidth. Then what is the selectivity and relation between bandwidth, selectivity and this is important. Even last, I think 2024 or 23, based on these relations also question is framed in GATE exam. Okay, so that you have to see in the next coming sessions, friends. Then after that, I have to give relation between damping ratio and quality factor. Then we'll solve some problems. Then we'll start the parallel resonance. This is about the session. Thank you. I'm ending the session.